Hi, and welcome to Week 14 Mini Lecture 2 for the Quantum Universe for Educators. In this mini lecture, we're going to talk about Feynman diagrams. So Feynman diagrams are one of the most important tools in quantum field theory. In quantum mechanics and quantum field theory, any process that happens in all possible ways at once. And there are usually an awful lot of possible ways that something could happen. And Feynman diagrams were diagrams invented to keep track of all these possible ways. Specifically, they're diagrams that represent processes that involve particles scattering off each other, so particles interacting each other via the fundamental forces of nature. So these are the rules for Feynman diagrams in quantum electrodynamics, the quantum field theory that tells us how electrons and photons interact. In other words, how electromagnetic fields interact with matter. Other quantum field theories that describe the other forces of nature tend to have slightly different rules, but they're pretty similar. So in Feynman diagrams, matter particles like fermions, which would be electrons in quantum electrodynamics, are represented by lines with arrows on them, whereas bosons, the forces, which would be the photons in quantum electrodynamics, are represented by squiggly lines like this. And they can point in any direction. The second rule is that you can only connect two lines with arrows with one wiggly line. And the point where they meet is called the vertex here. And one of the arrows must point into the vertex and one must point away from the vertex. Right. So every single vertex you see has to have one arrow going in, one arrow coming out, and one squiggly line coming out. No other possibilities are allowed. Now, every line that you draw must connect to at least one vertex. Okay, so you can't have just single disembodied lines, like the diagram on the right here. And we're only interested in the start and end points of each line. The actual paths themselves don't actually mean physical paths. They're not meant to say the electron travels along this exact path here. Right? So there's no point drawing messy or complicated looking curvy lines like the diagram on the left. You should straighten everything out so all the lines and all these squiggly lines are straight. So it's a useful exercise to go through, say, these three diagrams and explain what rules are being violated. I'll leave that up to you to do. Now, in diagrams, you tend to read them left to right or bottom to top. In the ones that we're going to look at today, most of them we're going to read left to right. And the direction that you read them is the direction of the time axis. Right? So time points from left to right. So as you go from left to right, you're going from earlier to later times. Now, antiparticles are represented by arrows that point in the opposite direction to the time axis, which seems on these diagrams to suggest they're traveling backwards in time. This should not be taken literally. This is just how you tell them apart from regular particles. So this positron here, the anti-electron, which is represented by an arrow pointing to the left, is actually a positron that is traveling to the right, that is traveling forwards in time. So bear in mind that although the arrows for antiparticles point backwards in time, the antiparticles themselves are still moving forwards in time. So some of the simplest diagrams that you can draw are shown here with their physical interpretation. So you read left to right. So here in the first diagram we have an electron coming in, it emits a photon and continues on its way. In the second diagram here we have a photon coming in, we have a positron coming in. We know it's a positron because the arrow is pointing backwards in time. So a positron comes in to meet a photon. That photon gets absorbed by the positron, which continues moving forwards in time. In this third diagram here, we have an electron coming in, and in this third diagram here, we have an electron coming in, meeting a positron, and they annihilate and turn into a photon. Whereas in this fourth picture here, we have a photon coming in, and it turns into a positron and an electron. Okay, Here are a couple more examples. In the diagram in the left, we have a positron coming in and an electron coming in. They annihilate to produce a photon, and then that photon turns back into an electron and a positron. So this is one way that an electron and positron can interact with each other. There's a second way though. You can have your positron and an electron coming in, and the electron emits a photon which gets absorbed by the positron, and the electron and positron continue on their way. In both of these diagrams, you start off with an electron and positron coming in, and you end up with an electron and positron moving away. In an experiment, there's no way to tell which of these two diagrams actually happened when the positron and the electron interacted. And in quantum theory, that means that both of these ways happened, right? Both of these contribute to the probability of an electron and a positron interacting. Here's a quick example of a Feynman diagram for a weak nuclear interaction instead of an electromagnetic interaction. This is one of the possible ways a nucleus can radioactively decay. Right? This is so-called beta decay, in which you emit a beta particle or an electron. And what happens is a neutron comes in here and it emits a W- particle, and that turns the neutron into a proton. The W- particle then turns into an electron and an antineutrino, which move away. Okay, the other useful thing about these diagrams is that you can take a diagram and you can translate it into a mathematical expression which you can use to calculate the probability for the particular process. So you can actually use these diagrams to do calculations and get concrete numbers out that you can then test with experiment. The math can still be a little tricky, so the examples I'm going to give are going to be fairly schematic. They're designed just to give you the idea of how this thing is actually done by people who work in this field. So if we take the diagram that we've encountered before, an electron and a positron come in, interact, turn into a photon which turns back into the positron and the electron. And this diagram has two vertices which I've labelled 1 and 2. So I'm going to use the rules that you'll learn about in the reading this week, specifically in the article Physics and Feynman Diagrams by David Kaiser. So according to the rules that you can find there, the amplitude A, which is just another way of saying the probability that this process will occur, is given by this expression here. So what you do is every time you see a vertex, that corresponds to a factor E, where E is the electric charge on the electron, times D, where D is simply the probability that an electron and a photon will meet and scatter. So this first vertex gives a factor E times D. After the first vertex, we have the photon, which travels between 1 and 2. So for every photon that starts with a vertex and ends in a vertex, this is a so-called virtual photon, you write down a factor C, and in parentheses, you write down the number corresponding to the vertex you start from and the vertex you end up. So this is C12. And C is the propagator, the probability that a photon travels from 1 to 2. And then finally you have another vertex, which gives you another factor of E times D. So multiplying all this together, then the probability for this whole process to happen is simply E squared times D squared times C12. Again, the numbers that these represent, or the equations that these represent, you can get from the full quantum field theory. But this allows you to directly calculate the probability of this process. All right, consider a slightly more complicated chain of events. Okay, so we're going to take the process that we just saw and we're going to tack onto it another process where the electron that emerges emits a photon and continues on its way. So there's a third vertex that is introduced here. So because the first two vertices and the photon that travels between them are the same as before, then when we write down the probability that this whole process will happen, we're going to start off with the same three factors as before, a factor of ED for the two vertices and a factor C12 for the photon travelling between 1 and 2. But now we get an electron travelling between two vertices. This is a virtual electron, and the probability it travels from 2 to 3 is given by the electron propagator, which we call B23. And finally, we have a third vertex, which means we have a third factor of E times D. So this probability, the probability for this event to happen, you get by multiplying all these factors together, and you end up with E cubed D cubed times C12 B23. And that is how you do quantum field theory, in essence. Now, the factors of E that you see in these probabilities, E cubed in this one and E squared in this one, are very important. There is a fundamental constant of nature called the fine structure constant, which is proportional to E squared. And the fine structure constant is approximately 1 over 137. So if you have a probability that is proportional to E squared and another process whose probability is proportional to E to the 4, that second process is much less likely than the first process. And we'll see how that is used in a minute. Now, I mentioned right at the start of this class that quantum field theory is the most successful physical theory of all time. It has been tested to the most decimal places. And in particular, you can use the magnetic moment of the electron, which is simply how an electron interacts with a magnetic field. You can measure that, and that actually gives you a measurement of this fine structure constant. Now, you can calculate it from theory using quantum electrodynamics, and you get this number at the top here, 137.035999709, with an error of 96 on the last decimal point, the last decimal place. Experiment has so far measured it to be 137.035999878, with an error of 91 on the last two decimal places. So these two numbers agree with each other to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 significant figures. No other theory has been tested this precisely. Now let me talk about how you actually calculate this. Now, an electron interacting with a magnetic field is described in the simplest way by this diagram here. All right, an electron comes in, exchanges a photon with our instrument that is measuring this interaction, and continues on its way. But this is not the only way that this interaction could happen. It could be that an electron comes in, emits a photon, and then emits a second photon, and then reabsorbs the first photon. All right, this obeys all the rules of Feynman diagrams, and therefore it is a process that can happen. But here there are 3 vertices, and each vertex contributes a factor of E, so the probability is proportional to E cubed. The probability of this simpler diagram was just proportional to E. So this is E squared less likely. E squared is proportional to the fine structure constant, so this process is 137 times less likely than this process. But it'll still happen. And if we're measuring it, the probability to so many decimal places, we have to take this into account. We also have to take into account even more complicated Feynman diagrams like this. All right? The electron could come in, emit a photon, which turns into an electron-positron pair, which exchange a photon, and then annihilate into another photon, which gets reabsorbed by the original electron, which in the meantime has emitted another photon, emitted a third photon, and absorbed that second photon again. Right? Or you could have a process like this, which I won't describe since I'm running out of breath. These are 4 loop diagrams because if you count the number of closed loops in them, you'll find that there are 4 of them. Each of these diagrams has 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. So the probability for this process is proportional to e to the power of 9. So these processes are 137 to the power of 4 times less likely than the simplest process. But again, we're measuring this interaction to such accuracy that we need to include these in our calculation. Now, the magnetic moment of the electron, if you calculate it, is equal to 2 times this number here, which is close to 1. Ordinary, regular quantum mechanics predicts that it is exactly equal to 1. But quantum field theory says no, because there are all these other processes, there are all these other ways that the electron can scatter and interact with a magnetic field, right? These weird, complicated ways. And we have to take them into account. These 4 loop diagrams here that look crazy actually make a difference when you go down to 12 decimal places. And if we didn't take them into account, we'd get the wrong answer when we compare to experiment. So experiment says that these weird, complicated processes here are also happening as well. That all these different possible ways an electron could interact with a magnetic field all happen at once, as weird as that is. And that is one of the most remarkable and well-tested consequences of quantum field theory.